Okay. Good morning, everybody. Okay. So it's a good time, so we can continue our lecture. So how was going on the last week's midterm exam? Is everything okay? Yeah. Hopefully you can solve the question easily. Okay. I think I did not give a very difficult question, so it should be fun, hopefully for everybody. Okay. So now we need to continue our lecture to 6-1. The MEMS design through foundries. Okay, so starting from today, last week we talked about previous weeks we talked about the design, what's the design process of the MEMS MEMS fabrication, MEMS devices, and also we compare with the IC fabrication processes, and also we mentioned about the different ideas, okay, among them. So now I will go on the MEMS design. If we want to do the design through foundries, so what will be the considerations for that? So first we look at what is a foundry. Okay, so a foundry is a fabrication service provider. Okay, so the foundry provide service of fabrication, and we give the designs, okay, to the foundry. So the foundry will collect different designs from different users. They put them together and to form masks. Okay, then the foundry company, they will do the fabrication service for everybody. So after you get your after the fabrication complete, they will cut the wafer into smaller pieces of chips. So each individual user will share one of the space, okay? Maybe one chips or two chips. And when you get the chips, you can do the further testing or other different things, or application. So the foundry means we can share the fabrication service together, because the fabrication is very, very expensive. It's not easy sometimes to do it by your own if you don't have a facility. Okay, so that's why the service provided for everybody. So for one wafer, for example, the 8-inch wafer, consists a large surface. So maybe your design need only a very small space, like 1 millimeter times 1 millimeter, or 1 centimeter times 1 centimeter maxima. So other space you can share with other like hundreds to thousands of people. So you share the cost together. So each of the individual will pay less amount of money. Okay, that's the idea of a foundry. So like TSMC, UMC, okay, those are big semiconductor fabrication company. They are foundries. They provide a service. Okay. So the advantage by using a foundry is we do not need to spend capital. We don't need to spend money for very expensive fabrication facilities. Okay, and it's very good for small volume. Okay, so if you don't need a lot of chips, typically like 10, 20 chips for testing. Okay, before you do real manufacturing for products. For couple chips for testing. So it's good to go to foundry to do this service. And this process is fast, and especially for prototype. Okay, so want to check out if your design is correct, you can use this service. So the turnaround time is usually around like 3 to 6 months. Okay, so we do not need to worry about the design or fabrication process and the yield of the process, because experts has taken care of this process. So we just need to do our design part, the MEMS design, circuit design, those part, and the fabrication part will belong to them. So that's a good thing. So in IC industry, people usually use foundry service or using the fabrication service. So they divide the designers and the fabrication foundry into two different groups. So people who know how to do the design, IC design, they may not know how to do the fabrication. So people who know the fabrication may not really understand the design, okay? Because the IC industry is a very mature industry. So they can divide into this kind of two different way to do the testing, fabrication and other fabrication and the design. So, but there's still some disadvantage when we talk about the MEMS fabrication, MEMS design, because as you know, the MEMS fabrication or design process need a lot of many different kind of complex way to do the fabrication. So when you consider to use this foundry surface, the fabrication process is limited. Okay, so you can use the process however the foundry or the vendor to provide. So if they don't provide this kind of fabrication you need to do it by yourself. That's for MEMS. Okay, so it's different. So the fabrication process, for example, is not flexible for wide experiments applications. And also the second issue is materials you can choose or selected are always limited. So not all the materials you can have. And also the device geometries are tightly constrained, okay, by the provided process, especially the thickness. So when we talk about the deposition of a material onto the surface, the thickness is usually limited because they fix the thickness of the fabrication. So we will have some idea later on, okay, when we talk about the CMOS process. So if we talk about you want to use it like a polysilicon, usually is 0.5 micron. Cannot be more, cannot be less. So the thickness is fixed. This is a kind of constraint. However, if you want to use like a polysilicon for like a 2 micron, even thicker, there will be problem. Okay. And also the post-process is sometimes very limited and difficult. So so-called post-process is after the foundry surface, you gather the chip. And actually, you have not finished your process. You have 2 more processes or 3 more processes to go. So you want to do it by yourself. But they will become very, very difficult because the turning back chips is very, very small. Only like a 1 millimeter size, okay, times 1 millimeter size. So you want to do the fabrication on this kind of small size chips. It's sometimes not very easy to handle. Yeah, it's like a dust, small dust. So, and also some post-process, usually the material or the process condition may not be compatible with the previous process condition and the previous processed material. For example, you want to do the high temperature annealing. Actually, it's not allowable after the turning back of your chip. Because some low temperature material has already been fabricated on your chip surface. So after the fabrication thoroughly finished, you want to continue to do like a high temperature process is not allowable. And also similar things. If you want to do very corrosive etching process, you also need to consider what kind of materials are already put down on the chip. So those things are limited when you want to do the post-process. And also, this kind of fabrication process may be good for some kind of devices, but not fit to all. Okay, so so that's why we need to understand what kind of fabrication process we can get from foundry, and what kind of material, and also the thickness from the foundry. Then we will consider if this foundry process suitable for our current design or not. If not, maybe we need to choose other foundry, or maybe we need to consider do it by ourselves. Okay, so that's a different things. So for IC and MEMS foundry, IC foundry is more mature than MEMS foundry, and for few variations, because when we compare IC and to MEMS process, actually IC process is not that complicated actually. So when you talk about the shape, the IC only uses several like a rectangle or line, this kind of shape. So if you want to use like a round or different the structure size, the IC foundry usually they don't consider that kind of situation. But for MEMS, a lot of different kind of material and shape structure can be used. And also, MEMS sometimes will involve some post-fabrication, including like a releasing process. Because MEMS talk about the movable structure. For the movable structure, after the fabrication, you need to release the structure from the surface. The releasing usually is a problem, actually, during the MEMS process. If you have taken the course about the MEMS fabrication, we will talk something about this afternoon. When you really deal with this kind of releasing process, sometimes the structure becomes very, very fragile, easy to broken. So not easy to handle. So that's the difference between the IC and MEMS foundry, MEMS process. So MEMS process is more complex, actually. Okay, so talk about the MEMS foundry. Actually, we have several different foundries. Okay, so actually this course will based on 2 foundry process. Okay, to consider how to do your design. So some specific structure or devices in this course, we will teach you how to use the foundry surface to do the design. But afterward, if your design or your process or your device structures is different, cannot be fabricated by those foundry process, you need to consider by doing that by your own. Okay. So that's for future. So the first one we will talk about is by using the most mature the IC process, the CMOS process. So there are many CMOS process providers because it's a huge IC industry now. So in this course, we will consider a little bit older one because the current IC process, the feature size can go down very, very small. So currently they can go down like tens of nanometer. Okay, in the future, they are going below 10 nanometer. I mean the feature size. So in this case, actually for MEMS process, usually we deal with the scale size around like a micron, even up to millimeter size. So that kind of small size actually in MEMS processor is not our MEMS device is sometimes not necessary. So we will use the like 2 micron process. That will be more than enough, okay, for most of the MEMS design. So, for example, like a MOSIS, the orbit is a MOSIS process, like orbit, HP, they provide a similar process. So the MOSIS process is based in the United States, similar to TSMC's process. Okay, so the surface is around like if you want the aerial, like a 1 centimeter square aerial, it will cost you around like 10,000 US dollars for that kind of size. It's not very cheap. It's not cheap. It's quite expensive. And if you use a TSMC process, similar, it's a little bit cheaper, but it's similar. So usually for the MEMS foundries, we will design the aerial sizes around like a millimeter size. So for millimeter size, you should only like a couple thousand US dollars. That's affordable for everybody. But for MEMS devices, sometimes you need a larger surface because you have larger devices, much larger than IC. So it's costly. Okay, it's costly. Okay, for example, like give you some basic idea. So for the MOSIS, okay, or the CMOS process, what kind of material and layer they can provide, and what kind of structure you can have. Just give a rough view here. Okay, so we will talk about in more detail later on. So look into the CMOS process. Actually, on the right-hand side, the total material you can get from the CMOS process is around like a 5.7 micron total thickness. It's not thick. Actually, it's not very thick. So when you look into the material, you have you can have like 4 different layers of oxide, silicon dioxide. Starting from the first layer, the field oxide. Field oxide is around like a little less than 1 micron, 0.85 micron. Then you have 2 more oxide layers, silicon dioxide layer. That's for the insulator between 2 electrodes. You have 2 layers of metal electrodes. Okay, 2 layers of metal, like aluminum electrodes. You want to connect the signal to outside. So you can have 1 go horizontally, the other one goes straight, go the other direction. So you can take out all the signal out. So two metal process. Actually, two metal process is an old process. Currently, like a TSMC, provided the metal layers can be more than 6 layers, even 8 layers. Very, very thick. Okay, because they have a lot of connection in a small area. So they want to fan out to outside. They need to have a much more layers to provide the signal fan out process. But for this one, there are only 2 metal. Here, 2 metal, metal 1, metal 2, and 2 oxide to separate them. Then on the top, there are another silicon dioxide as a preservation, as a protection. So the top over glass, it covers the whole chip for protection. So that's all the materials you can get. Oh, another one, sorry, I forgot the polysilicon. For polysilicon, those materials are on the gate. You provide a signal to the gate to control the transistor, the gate of transistor. So you have the polysilicon. So there are 2 polysilicon layers. So those are polysilicon. You can use them as a material, also a structural material. So those are all the materials and all the thickness you can get from the IC, especially CMOS process. Okay, so it's not thick. So if you are consider using very thick structure, sometimes it's trouble. Okay, it's a problem. So if you take out some material, you selected only a couple material. For example, all the oxides stacked together is only 3.18 micron. Only 3 micron. So for example, in the first, maybe next week, we'll start to discuss how to design a accelerometer. So for a accelerometer, we usually use the stacking of 4 layers of the silicon dioxide as a cantilever beam structure. Okay, so the total thickness is only 3 microns, pretty thin. Okay, even you add 1 sensor layer, like polysilicon on the left-hand side, as the inside the structure. So totally you have only 3.5 micron, roughly. So it's not thick, actually, very thick for all the purpose. So if you want to consider put a large proof mass underneath this kind of cantilever, so sometimes you need to consider using different material, different structure to put them together. If you want to use all those materials, not thick enough actually. But they are okay for fabrication of the cantilever structure, for thin structure, but it's okay. Or bridge or membrane structure. So this is a cross section of all the materials stacked them together. So they are possible to form the structure underneath. Okay, for example, the black one represented the metal. So you have 2 metal layers. The metal can connect to the bottom by puncture hole on the previous layer. For example, this one is the metal 1 layer. So you want to connect the metal 1 to the active region. Okay, so you need to form some hole, via hole, okay, on the first oxide layer. Okay, so when you puncture hole originally on the first oxide, then you deposit metal fin on the surface. The metal fin can go into, okay, the hole and do the connection automatically by themselves. Do you understand? So this structure is formed in 1 fabrication process, 1 deposition process. But in the previous process, you need to punch a hole, make a hole, okay, on the previous layer, the insulation layer, the silicon dioxide layer. Then you deposit the second one, they will connect automatically. So the same applied to the metal 2 layer. So in the metal 2 layer, you also punch a hole on the second oxide layer. So when you deposit the second metal, there will be a connection, okay, from the second metal to the first metal structure, okay. So on the bottom, all those structure, almost parts structure or PMOS structure, actually we introduced previously. So you may have some idea, okay, about the structure. So there are source, gate, and a drain. Three different electrodes connect to them, okay, for the operation. So this is the structure we are going to use for the next like 3 weeks to design a real accelerometer, workable accelerometer. And then your two homework, you also will do the practice. Actually we will use the software, the edit software we introduced a couple of weeks ago. Use that to draw the layout. Okay, after you finish the design of the structure, the size, you need to draw them onto the ground level, and to see the structure stick by layer by layer. Okay, so those things you need to practice. So after finish the design, actually the design layout file, you can send it out to the mask fabrication or send out to Foundry. The Foundry will fabricate the device for you. Okay. Okay, so by using this simple structure, actually there are many MEMS devices we can fabricate it. Okay, for example, like the cantilever beam. Okay, and also the flow sensor. Flow sensor is like a membrane. Okay, it's underneath it is empty. Okay, so the membrane suspend on the top of the cavity. So all the sensing part can be fabricated inside the membrane, okay, on the top of the membrane, okay, inside the device. So those things, you look at from the cross section, they are very thin structure, okay. So they can do like a cantilever or suspended membrane or bridge. So those structure can be fabricated by using the CMOS or the MOSIS foundry process, okay. Just give an example. So in your first, the first homework, so we will practice how to design a flow sensor combined with the IC together, using the IC to drive microflow sensor. Okay, so you will use both of the knowledge of the IC, a little bit IC design fabrication, and also the MEMS fabrication together, and to design your own the first flow sensor, these kind of simple things. Actually, it's not really design, it's just do estimation, actually. The design has been provided by the homework, actually. You just need to fill in what kind of size you need. Just do simple calculation according to the equation we provided here. Okay, so the real design will be later on when you are considering design or like an accelerometer in a specific application. So they will give you different specs. So that you need to consider thoroughly from the beginning to the end. But for the first homework, for the first homework, we just need you to do some simple calculation. Okay. This is a beginning, so we need to have some practice. So this is the first one. The second one will be the MEMS process. MEMS means the multi-user MEMS process. So the MEMS process is specially designed for the especially surface micromachining people. Okay, so different from the IC, the MOSIS process. The MEMS process, especially surface micromachining process, usually use polysilicon as a structural material. So to provide more flexibility on the polysilicon, so they provided 2 layers of polysilicon with a thicker structure. For example, the first poly, the poly 1 is 2 micron. So compared to the CMOS process, the polysilicon layer is only 0.4 micron. It's much thicker. So the first polysilicon can really give you much more flexibility to do thicker structure. So it's a poly 1. And in addition to the poly 1, they also provide poly 2. The poly 2 layer is also very thick, 1.5 micron. It's much thicker than before. So if you combine these 2 polysilicon layers together, the total thickness will be 3.5 micron. So 3.5 micron, consider the thickness is much thicker than the whole layers are sticking together than before. For example, like this part. Okay, so you have a structure layer much thicker than before. So it's easier to use. And the fabrication process, the cost is a little bit cheaper. Yeah, it's around 3,000 US dollars per centimeter square. Okay, so it's affordable for most of the lab. Okay, so because the MEMS structure usually is larger than IC, so we talk about the size. Usually, the return size of the chip is around like centimeter size. It's not a millimeter size. For the CMOS, usually they will give you like a millimeter size. It's pretty small. But for MEMS process, usually you can get like centimeter size chip. Okay, so in addition to the structure, major structure, poly 1 and the poly 2, so there are also some other insulator or superficial layer structure. For example, the oxide 1 and oxide 2. So the oxide 1 is the first superficial layer. So it consists like 2 micron thick. Okay, so the first polysilicon is 2 micron. So the thickness for the first superficial layer and the first structure layer, they are compatible. Okay, both of them are 2 micron, so they are compatible. But they are very thin oxide layer between the poly 1 and the poly 2, only half micron here. Okay, so you have some flexibility to separate the poly 2 to poly 1. Also, if you take out the oxide 2 layer, you can connect them together, become a thicker structure. So this will give you a flexibility to either separate these 2 layers or connect these 2 layers together. Depends on your design and your need. Okay. So those are major structure material. So polysilicon is a major structure material, and the silicon dioxide here is using PSG. It's a kind of very fast etched material. So we can do the superficial etching process easily because this oxide layer can be taken away quite quickly. So in addition to the structure material, the MEMS process, multi-user process, also provided like the signal connection. So there are 2 types of signal connection. One is from the bottom. The other one is from the top. From the bottom, you can see there is a poly. Okay, this thin polysilicon layer, we call the poly 0, is only half micron. So this poly 0 is not used as a structure layer. So the poly 0 is used as an electrical connection, connect signal into the device. Okay, so we call the poly 0. It's not used for fabrication of the structure. And on the bottom, we have the silicon nitride. It's a low-stress nitride. It's a very thick nitride, 0.5 micron. So the purpose is for insulation, for preservation. So to prevent the electrical connection between the poly 0 and also the substrate, they separated the electrical connection, okay, by using a very thick silicon nitride. So maybe you will ask, well, why we need this kind of very thick silicon nitride as an insulation? Usually like 100 nanometer or 0.1 micron might be enough. Why do we need that thick? Because in the process, we will talk about this process in more detail later, consider a lot of a dry etching process. So each time you have a dry etching process, the dry etching does not give you a very strong selectivity between different materials. So the bottom, the silicon nitride structure will go through a lot of dry etching process. So they can maybe consume away easily. So that's why we need a very thick silicon nitride layer here to have enough protection, okay, to the substrate. Okay, so this is one of the electrical connection on the bottom by using poly 0.